Hi, this video is about the factors that influence the strength of gravity. But first, I was thinking about bonfires. What determines the strength of a bonfire? If we're thinking scientifically, you got to think about the amount of fuel that you have, how much firewood do you have, and how dry it is. But more than that, the strength of a bonfire is really in how many marshmallows you have and how many friends you have around the bonfire. What determines the strength of, let's say, a cookie recipe? Now, without question, the strength of a cookie recipe hinges upon the number of chocolate chips that are present. I would also say that the strength of a cookie recipe is dependent on the amount of butter that you put in, and especially the lack of raisins in the recipe. All three of those things, I think, are really influential in the strength of a cookie recipe. But the subject of this video, the real subject of this video, is what determines the strength of gravity in nature. What makes gravity stronger or weaker? And there's actually only three factors that determine the strength of gravity. So what are those three factors? Oh no. Oh man, I'm making all kinds of mistakes right now. I hit my camera so many times. All right, how does this look? That's not good. All right, so what determines the strength of gravity between two objects? Now, Isaac Newton discovered that gravity exists between any two objects in nature, and the amount of gravity is dependent on three things. The first is the mass of one of the objects determines how strong gravity is. Bigger means more gravity. The second is the mass of the other object involved in the gravitational interaction. So both of the masses influence the strength of gravity. And then thirdly, it's the distance between the centers. Now this has an inverse effect. If the distance is greater, the gravity is weaker. And this follows actually an inverse square law, so that as you get further and further away, the strength of the gravity drops off exponentially. So to put this all together in a relationship with mathematical symbols, we have the force of gravity, and this symbol means proportional, or is related to. The force of gravity is proportional to the product of the masses divided by the distance squared. So if you have a big distance, that's going to be a big denominator, which means a weaker gravitational force. And then in the numerator, masses. So more mass means more gravity. More distance means less gravity. Let's look at a few examples of this with some numbers. So let's say you have a tiny moon that orbits around Jupiter, and it experiences a force of 48 newtons. Tiny moon. 48 newtons is not much at all. I just made it this way to make it a simple kind of example here. What gravitational force would this moon experience if the moon, let's say, had twice as much mass? Okay, so remember the relationship here. The force of gravity is proportional to the mass of both objects here, Jupiter and the moon, divided by the distance squared. So the mass of Jupiter here, I'm going to leave unchanged. We're going to be talking about the mass of the moon changing. And then also the distance is going to change in these other examples. But for the first one, just the mass of the moon changes, and it is twice as much mass. So twice as much, that's going to be times 2. And so the way that the newtons would change here, the force of gravity is going to be 48 is the original, but it's going to be times 2. Because of the mass getting multiplied by 2. So 48 times 2, it's going to be 96 newtons. My marker is dying as well. What if you had the same mass as the original moon here, but the distance was twice as much from Jupiter's center? So if you double the distance, remember, if you double the distance, that's going to result in the gravitational force being weaker by the inverse square. So doubling the distance, if you do the inverse square of that, that's going to be 1 over 2 is the inverse, and then squared, 1 over 2 squared, it's going to be 1/4. So it's going to be 1/4 times 48, which is going to be 12 newtons. So we've done, again, inverse square of the distance. So 2 is twice the distance, inverse square of that is 1/4 as much. What if the moon had the same mass, but instead of twice the distance, what if it was 4 times further away from the center? So much greater. Well, now this 4 inverse square of that is going to be 1/4 for the inverse squared. That's going to be 1/16. So the gravitational force is 1/16 as strong now. So 1/16 times 48, that's just going to be a measly 3 newtons of force. And then finally, what if we had 2 changes happen? What if we had twice as much mass, but it was 1/2 the distance? So you're actually getting closer to the planet. So if you have multiple changes happening here, then you're going to have to multiply your factors together to figure out the overall result. So twice as much mass is going to be, 2 times the gravitational force. 1/2 the distance, that means you're getting closer to Jupiter. So it's going to be stronger as a result. So 1/2 inverse square of that. The inverse of 1/2 is 2/1 squared, which would just be 4/1. So combine these two together. So 2 times 4/1, or just 4, times 48. So after doing that math on a calculator, is 384 newtons. So that's a much greater change here because you've done 2 changes, twice the mass and 1/2 the distance. That's all I've got for you in this video. Remember, this day could be your last, so live on purpose.